When we model average cost functions, we end up with an asymptote that's neither horizontal nor vertical when we approach infinity or negative infinity. And this is called an oblique asymptote. And when I go through the example, I'll show how that's very easily found. So the first thing this is asking us to do is we are given a cost function, and we need to use the graphing strategy to analyze the graph of the average cost function. So the first thing you need to do is write the average cost function. So it's going to ask you and require you to recall. And average cost function is just the cost function divided by x. And we can write this as 1,000 over x plus 0.5x. The domain of this needs to be all positive reals, so x greater than 0. I think the vertical asymptote, we know that x equals 0, and because these are all has to be all positive, it's self-explanatory that we would have a vertical asymptote at x equals 0. But let's look at the other asymptote that we will have. When x approaches infinity, 5,000 over x is going to be really small. So what happens is we find that we have this oblique asymptote that will occur at y equals 0.5x. We'll see as x approaches infinity, we're going to get closer and closer to the line of whatever this is on the outside here, 0.5x. First step. Second step, analyze the first derivative of our average cost function. So the first derivative is going to be negative 5,000 or negative 5,000 plus 0.5x squared over x squared. So set the numerator equal to 0. When you do that, you're going to get x squared equals 10,000. Divide everything through by 0.5, or we'll just say 0.5, and then x equals plus or minus 100, and since our values must be all positive, it's just 100. And we see that less than 100, it's negative. Greater than 100, it's positive. So we're decreasing from 0 to 100, increasing from 100 to infinity, and 100 is a local min. Okay, now analyze second derivative. You get 10,000 over x to the third, and that will always be concave up. And let's not make that negative infinity, let's make that 0, because we know our lower bound is 0. So let's look at a graph. So I'm going to minimize all of this. Pull it over to the side so that I can graph this. So on my graph, I want and I'm going to count by 50s and by 50s over here. First off, I know that I have this oblique asymptote 0.5x, so at 100 it's at 50, at 200 it's 100. So this is my y equals 0.5x. Okay, and I know that I have a local min at 100. So we need to find out what is the value at 100. So when you substitute 100 back into your average cost function, you get 100. I know it's decreasing and then increasing, concave up. And if we were to ask the question, what is the minimum average cost? The minimum average cost is whatever you have found to be the value of your local min. And this just tells us, and there's one other thing I just want to evaluate. Let's evaluate marginal cost. Marginal cost is just taking the first derivative of cost function. So this would be x. If I graph that, we find now that the minimum average cost occurs when the average cost equals the marginal cost. Hopefully that wasn't too bad. Go ahead and do matched problem number 5. I'm going to zoom in so you can see the problem. And certainly you can graph it, but the main thing you want to be able to do is find the minimum average cost. So the matched problem, I have the quick answers there. You needed to find the average cost function. The oblique asymptote is there. If you want to graph it, certainly in order to solve the problem, you don't have to. But I will add that on here real quick. Maybe it makes it a little bit easier for you. I'm going to count by 20s, 24, 60, 80. And I'm going to count by 10s over here. And then I'll just do a quick graph for you. This is your oblique asymptote. (80-40). Y equals 0.5x. That on there. And then the actual graph looks something like that. Oh, sorry. Put it at the wrong spot. Let's try that up here. My bad. Okay.